I'm going to jump back into what we were talking about last time, which we had more or less finished chapter 27, but there's a few little concepts I wanted to make sure I hit you with before I jump into the more rigorous, difficult stuff of chapter 28. So I'm going to go ahead and start off sharing my screen. Does anybody have any questions before we get started? Okay. So as you see, I'm calling this finishing up chapter 17, magnetism. So first off, I said explain the velocity selector, which is and what is the velocity selected. So what I have here is a drawing. You can sort of look at those two purple lines with the pluses over it, and then the other purple line with the minuses below it. You can look at that like a capacitor because that's more or less what it is. But then you see you have two black walls on each side. The left hand side, you've got a black wall at the top and a black wall at the bottom with a little slit in the middle. And then on the right hand side, you have the same thing. And those two slits are intentionally lined up. So they're supposed to be something that will stop the individual particles. So basically, by putting that little slot in there, you're only going to get a fine beam of particles that come through. Not only that, you can use the velocity selector to take any velocities that aren't the correct velocity, plus or minus some error, and you can use the strength of the electric magnetic fields there to cause the particles to hit those black walls. So it'll only allow velocities that are very specific. To make it through both of those holes. The way it does that is, as you saw, the top plate is positive and the bottom plate is negative, so that establishes a electric field E pointing downward. The electric field pointing downward means that positive charges will be deflected downward, negative charges would be deflected upward. But if you'll notice, I also drew these little green X's, and that's supposed to represent a uniform magnetic field that points, excuse me, a uniform magnetic field B that points into the page. If you use your QV cross B, since this is a positive particle that I drew, the Q times V is the same direction as V, which is to the right, and that means my hand can be in any of these positions at once until I figure out what the magnetic field direction is. Now I know the magnetic field direction is into the board, so I turn my hand like this, and now my middle finger points down, my index finger points to the right, which is the direction of QV, and my thumb actually points in the towards the screen, what you're seeing here, but that means up in the diagram. So the magnetic field is going to deflect positive particles upward, and the electric field is going to deflect positive particles downward. So if you set the strength of the force of the electric field equal to the strength of the force of the magnetic field, then you'll get basically a relationship that's going to hold here if the object has exactly the right velocity. So we get, I'll write it here in blue in between the two. I'm going to say FE is equal to FB. That means the force due to the electric field is equal to the force due to the magnetic field. I've taken the time to write out what those forces would be. Notice in this case, Q times E is downward because Q is positive, and QV cross B is upward because Q is positive. So we can just set those two equal to each other. And since V and B are perpendicular, the QVB just becomes Q times V times B, because otherwise it'd be Q times V times B times the sine of the angle between the velocity and the magnetic field. But the angle is 90 degrees and the sine of 90 is 1. So with that in mind, I get QE is equal to QVB, like that. You can immediately see that the Q's cancel out. And by the way, if it was a negative charge, then that would cause the negative charges, the electric field would cause the negative charges to deflect upward, but the magnetic field would cause the negative charges to deflect downward. So this velocity selector actually works whether it's a positive charge or a negative charge. The only thing that we left off is the gravitational force, but as you've learned, the gravitational force compared to magnetic or electric forces is minimal, so you can pretty much ignore that. Plus, these particles are going to be going so fast that you're talking on the order of nanoseconds or maybe at best microseconds, and gravity doesn't have much of an effect over a time period of a microsecond. So, with that in mind, you now have E equals VB, and that tells you that specifically that the velocity that you've selected is in fact given by the magnitude of the electric field divided by the magnitude of the magnetic field. So that's how a velocity selector works. By choosing the E and B to have exactly the right ratio, for instance, if you wanted the particle to have a velocity of 3 times 10 to the 6 meters per second, then the magnitude of the electric field divided by the magnitude of the magnetic field should give you 3 times 10 to the 6 meters per second. Any questions on that one? All right. The next thing I wanted to do is explain the Super D's cyclotron. Your book sort of hints at that, and there's a later chapter where it actually has the drawings of the Super D's. But I highly recommend you just do a Google search for the word cyclotron and actually look at the Wikipedia page. It's actually really good. It's got some photographs of the Super D's, and it's got schematic drawing of the Super D's. But the way the Super D's work, and I'm sort of glossing over some stuff about how this initial particle gets in, so you can just sort of ignore that. But basically, what happens is a particle, let's say a positive particle with a velocity v, is going to enter this area right here that's shaped like a D. So this is one half of the super D's. This is the other half of the super D's. And you can see there's sort of a little box, if you will, that's shaped like the letter D. And then this one is also a little box that's shaped like the letter D, like that. So when the particle comes in here, it immediately runs into this magnetic field, which you can see represented by the little green dots in the center of circles. That means the magnetic field is coming out of the page. Okay. If we're imagining this as a positive particle, then at the top of the right double D, the particle is going to the right. And since it's positive, that means QV is also pointing to the right. So we point QV to the right. Now I've got to turn my hand so that I can orient my middle finger to point in the direction of the magnetic field, which is up. So I get that. And now what you see is when the particle is moving to the right, the positive particle moving to the right, the force is causing a downward force. It's towards me, but that corresponds to the downward direction on this iPad. So it's perpendicular to the velocity and it points inward. That means it's going to try to curve downward. And in fact, if you then say, okay, now the velocity is not exactly horizontal, it's horizontal and down a little bit, you still get a center seeking type force. So what happens, if I could draw the little forces in here, is initially the force is this way, but when the particle is moving this way, the force is that way, and when it's moving this way, it's that way, and this way it's that way, and this way it's that way, and this way it's that way. So you can see at all points along the circular arc, the force due to the magnetic field is pointing towards the center of the circular arc, so it's maintaining a circle. Well, how big is that circle? Well, that's part of the physics that we need to work out here. So what we know is Newton's second law says the summation of forces is equal to mass times acceleration. We can see that the only relevant force is the Q V B, like that, and that's equal to m. And then the acceleration, since it's going in a circle, the acceleration is going to be v squared over r. And what you try to do is make sure the b is strong enough that you can get an r that keeps it inside that d, basically. Okay, so now we can see that one of these v squareds is going to cancel out with one of those v's, and now we can say that the radius of the arc that the object's going to make is in fact mass times velocity over charge times magnetic field. So that's an equation you need to be able to come up with on your own, even though I think I probably, you can check your equation sheet for this to be certain, but I think I might actually put it on your equation sheet anyway. So you know what the equation sheet is. It's in our module, the useful documents and links module, and it's at the bottom of just about every practice test as well as every old test that you took. But that tells us what the radius are, or is. So you just need to make sure that your D's, whatever size they are, that once you figure out the mass of the particles you're using and the charge of the particles you're using, you want to make sure that radius is smaller than the radius of the d's in this case. Once you have that, then you can calculate things like the velocity and stuff like that. Remember, the velocity is actually given by velocity, since it's going in a circle, is the circumference of the circle, which is 2 pi r, divided by what we call the period, which is the time required for an object to complete a complete cycle. So, for instance, if it started here and it makes a complete circle, it's the time required for it to go from here to here again. That's capital T. So we've got V is equal to 2 pi r over T. And what that means is you can go ahead and plug in your velocity and or you could plug in your R in here, but the main thing is we're trying to figure out what the period of oscillation is. So if I wanted to plug in the V into the R equation, I'd say R is equal to M over QB, and then V is 2 pi R over T. And what you see here is the radius on both sides cancels out, and that, of course, leaves a 1 on the left. That means you can go ahead and solve for T. And in that case, you get T is equal to 2 pi times M over QB. So that's the period of oscillation of this particle. And the neat thing about that is that it doesn't depend on velocity. So if the velocity speeds up, which is the whole purpose of these D's, is it's going to speed it up. And I haven't explained how it's going to speed it up yet, but I will in a second. But since our job is with this cyclotron is to speed up the particle to go faster and faster and then ram it into another particle to, for instance, break up an atom or something, then it's really helpful that the period does not depend on the velocity, because the trick that we're going to use to speed this up is if it's a positive particle, they're going to make the right D, they're going to make that negatively charged so that when it goes across that little gap from the left D to the right D, it speeds up in that little space between the D's because it sees that negative particle in that frame of the D, and it's equally pulled to the front of the D as it is to the back of the D. So it, in that sense, it has no compulsion to go forward or backwards. It's just going to stay in the same plane, and it'll shoot right into the middle of the D or into the edge of the D. Then the magnetic field is going to whip it around like this, and then at half a period later, you're going to switch the polarity of the D's, where now the right D is going to be positive and the left D is going to be negative. So when it gets to that bottom gap, the left D is negative, and that's attractive to the particle. So now the particle is going to speed up across that little space again, and then it's going to hit another magnetic field and curl upward. And then a half period has gone by again. So now you flip the polarity. The right D is again negative, so it's attractive. It's going to speed the particle up through that gap. And you just keep going and going and going until ultimately it gets to a very high speed. That's the cyclotron, and that's pretty much how it was created. You also could figure out, for instance, the frequency, and we remember frequency is 1 over the periods. For instance, if you found that it takes, uh, if you found that one wave passes by you, like you're standing on the pier and you see the peak of a wave come under you at the pier, and then you count, and at the end of 4 seconds the next peak of a wave comes by, that means a whole wave has went by you in 4 seconds. So the frequency there is 1 wave per 4 seconds. That also means that the period of a wave, the time it takes for one wave to pass you by, is 4 seconds. So notice the period is 4 seconds, but the frequency is 1/4 of a hertz. So it's natural to reach the conclusion that F is 1 over T, or T is 1 over F. So with that in mind, we can also say that F is equal to 1 over 2 pi times QB over M. And that's pretty much all the real equations that you need for understanding cyclotron type motion. And that's part of what we wanted to discuss, just so you can answer these similar problems and solve problems like this. Another thing I wanted to do is explain the torque and potential energy of a magnetic dipole. So, a magnetic dipole turns out to be, you can think of it as a circular wire. You could have, for instance, a wire like this with a current going around it. And according to a right hand rule, if I curl my right hand fingers in the same direction as that loop is, then my right thumb points in the direction that's perpendicular to that plane. And that direction is the direction of what we call the area vector. Okay, so if I calculated the area inside of this loop of wire, that area would be pi r squared. So what I would do is make that vector A have a length of pi r squared, and it would stand perpendicular to that. Additionally, if it was more than one wire, so for instance, the wire made one loop and then it came down and there's another wire that made another loop that was the same size, and then another wire and another loop. In that case, you have more than one loop of wire, you have, let's say, n loops of wire, then in that case, you get that the magnetic dipole moment is n, the number of turns, times I, the current going around it, which I didn't label on here, times the A vector, which I should keep the purple, times the A vector, which I just explained, fit a right hand rule. Okay, so again, if you see the loop of wire curling this way, then you want to take your right hand and make sure it curls that way. If you see the current going around the loop the other way, then you want to curl your hands that way, and the right thumb is going to point the opposite way. So that's how you actually calculate the dipole moment. This is equal to the magnetic dipole moment. And you should be able to see that the units of that would be, for instance, amps times meter squared. Amps meter squared is the magnitude of the magnetic dipole. That's the units of it. Now, I want to consider a very simple case of a dipole that's made out of a square loop. So let's imagine we have a wire that comes up this way. It's carrying a current I. So current I is going into it, and it runs along a little piece of metal that we're going to treat as an axle. So here's a little axle, and that axle has the ability to rotate, of course. I'm going to take this wire and run it around or alongside this axle, and then the wire is going to go off, and then it's going to hang a right, and then it's going to go again about this far. I'm trying to make it really symmetric, and then the wire will come back and go this way so that the current will come out this way. So what we have is a current that's going around this wire in this way. And we're going to say this dimension right here is A, and this dimension right here is B. Okay, so that means the area is equal to A times B. Now, if we imagine that this actual current carrying wire is immersed in a magnetic field, then we might say, let's assume, for instance, that the magnetic field is uniform and points from left to right. Okay. Well, if you look at the bottom wire, the current is parallel to the magnetic field. So we know the force on a current carrying wire is given by F is equal to IL cross B if the current doesn't have a change in relative orientation relative to the magnetic field, and the magnitude of the magnetic field doesn't change, and the magnitude of the current doesn't change, and the length of the wire doesn't change, then we can just use IL cross B instead of doing that differential stuff like we did last time. So, with that in mind, you can see that when the current is parallel to the magnetic field, that means L is parallel to the magnetic field, and that means that there will be no force on this wire. There will be no force on this wire, and there will be no force on this wire. So the only forces are going to be experienced by the vertical wire going up and the vertical wire going down, the current going up and the current going down. So now I'm going to use F equals QV cross B to figure out the direction of the force on the left wire. So QV, remember we pretend current is conventional current, and that means positive charge is going up on that left wire. So QV's up. The magnetic field points to the right. As long as I just know the current, then all these positions are fine for my QV. But now that I know the magnetic field is to the right, I have to turn my finger around until my middle finger points to the right. In this case, I'm lucky in that the middle finger, which represents the magnetic field, and the index finger, which represents the current, are at 90 degrees, specifically because the current and the magnetic field are at 90 degrees from each other. And this tells me, in fact, that the force on the left-hand wire will point into the page. So this is FB on that wire. Now, if I do the same thing for the wire on the right, in that case, QV is down, B is to the right, and now I see that the thumb is pointing out of the page. So on this side, the force is going to be out of the page. So that tells us that that loop of wire is going to tend to rotate like this. In other words, the right face is going to come out of the page, the left face is going to go back behind the page, and then it'll line up so that the magnetic field goes right through the hole in the middle, and it'll keep doing that. But the main thing is you see that because it's pushing into the page on the left and out of the page on the right, that tells you that this object is actually going to tend to rotate the opposite direction I drew. So let me fix that real quick. That means this whole thing is going to tend to rotate that way, which means, again, if we were looking from above, that would be a counterclockwise rotation. If we were looking from below, it'd be a clockwise. So let us calculate that torque. Well, we can calculate the torque because torque is equal to R cross F. In this case, the F is just going to be the QVB, as we already talked about. But what we need is the R cross F to get the torque. Well, the torque is also written as, if you want to write it just a magnitude, you can also write that as R perpendicular times F, or you can write it as F perpendicular times R, or you can write it as R times F times the sine of the angle between them when the two vectors are tail to tail. The main thing, though, here is that we know the torque is going to be represented by a lever arm that goes from the center of the axle to here. That's the lever arm. So the torque on the left one is going to be A over 2, that's the lever arm, times the force, and we know the force is going to be I times the length of that wire, which is B, times the magnetic field, which is capital B. So that's the torque on the left, and it implies a counterclockwise rotation as seen from above. And the main reason I'm saying that is because we got to keep in mind, do these two torques fight each other or are they contributing to each other? They are actually contributing to each other, but I wanted to make sure we knew that. So now I'm going to do the torque on the right side. That one also has a lever arm equal to A over 2. And it also has a current I going through it. And it also has a length of wire B, and it happens to be in a magnetic field B. Okay. Now, if that happened to be instead of just one wire, it went up and then went around, n times, then the number of wires would be n, and you'd have n times I as opposed to just I. But either way, we see that this also causes a counterclockwise rotation as seen from above. So these two torques are helping each other, and that tells us that the torque total is equal to A over 2 IBB plus A over 2 IBB, which equals I times B, or excuse me, I times big B times AB, and AB is the area of the actual dipole. So that tells you that the torque total is equal to I times A times the magnetic field. And in fact, you know that it's going to change in angle. And if you had it at a tilted angle instead of the current being exactly perpendicular to the magnetic field, you could actually figure out that this turns out to be torque is equal to mu cross B, where mu is equal to n times I times the A vector. So that's the magnetic dipole torque, and that's a vector symbol that should be on top of that. And you'll notice that looks a lot like what we found for the electric field when we found that the torque on a electric dipole, which was P, was equal to P cross E. Now, you can also do the calculate the potential energy. I'll leave that one up to you reading your book, but it turns out that the potential energy is equal to negative mu dot B. Okay, and that is just like the fact that the electric field had a potential energy, or excuse me, the electric dipole had a potential energy given by negative P dot E. So you can see that these two formulas work out to be very, very similar. And this is just us building up to pointing out to you guys that the electric field is really just one side of a coin that is made up of the electric field and the magnetic field. And literally, there's some cases where you can choose a reference frame in which the problem you're trying to solve only has an electric field and it behaves a very specific way that you can calculate. But if you jump to another inertial reference frame, one moving with some velocity compared to the last one, for instance, in that frame, if it's chosen right, you'll have only a magnetic field, and you do an analysis and you get exactly the same motion, only that motion came from a magnetic field because there was no electric field. That's what we mean when we say that the electric field and the magnetic field are just two sides of the same coin. But this is you seeing all that. So those are equations you're supposed to be able to use. I will tell you to check out the mass spectrometer as well. Just like we were able to use the equations QV cross B and MV squared over R and all that good stuff, we can use all those to actually imagine individual isotopes, say, of uranium. If you were wanting to, for instance, split up uranium-235 from uranium-239 and all those different isotopes of uranium, then you can subject it to a magnetic field and electric fields if you want to isolate the speeds. You can use a velocity selector, and then you can send it into a magnetic field, and the different masses of the isotopes will cause the radius of the arc that it makes to have a different radius, so that you get basically one radius for a small mass, and then a bigger radius for a bigger mass, and then a bigger radius still for a bigger mass still. And all you do is you set up a collector at the radius that you want. For instance, you might want uranium 235 instead of uranium 239, and you work out the math and figure out exactly what radius the U 235 would have, and you put your collector right there at that radius, and that allows you to separate out the isotopes of uranium 239 from uranium 235. That's how a spectrometer works, but it works on these same principles. I'm not going to make you, solve equations using the exact equation that they had in the mass spectrometer part, but I want you to understand that that's how it works and that it's more or less the same thing, or it's very related to the velocity selector. Another thing that I wanted to point out is if you happen, your book actually asks you to do this. It says conceptually, uh, what is the motion of a particle that encounters a magnetic field? Let's say the particle is shooting straight towards the screen and it encounters a magnetic field pointing to the right. Well, what's going to happen is if it's a positive particle, then QV points that way and B points that way according to my pencil. So that means that particle is going to feel a force downward. That particle is going to start to dive downward, and then it has QV pointing that way. Again, B is this way, and you see that still the force is perpendicular to the velocity, and that's going to make it point further down and further down and further down. So basically, what's going to happen is you're going to get the particle going this way, and then it hits a magnetic field and it makes a circle. You can calculate using those equations that I just showed you, R equals mv over qb. You can calculate the radius of that circle. But here's the neat thing. You can calculate the radius, you can calculate the frequency, you can calculate the period, all from those equations I just gave you right there. But if it happens to have a particle that's not just a velocity straight towards the screen, let's say it has a velocity a little bit to the right and towards the screen. Well, that velocity to the right is parallel to the magnetic field, so no force is assumed from that one. So what happens is the particle, which was originally, we were talking about it just going straight towards the screen, now it's going to go a little bit this way. But what it's going to do is it's still going to take that component of velocity that's towards the screen and make it go in a loop this way. But the velocity that's to the right, the component that's to the right, that's going to make the particle completely drift to the right, to the right, to the right. So what'll happen is the particle will do a circle as it drifts to the right, and then it'll be at the top of the circle again, only it's not in the same spot that it was because it's moved to the right, and then it'll do another circle and another circle. So it basically traces out a helix or a spring, sort of like a slinky or something like that. That's what happens to particles when they have a component of velocity perpendicular to the magnetic field, causing it to circle, as well as a component parallel or anti-parallel to the magnetic field. That'll make it travel along the magnetic field. And you'll see that your book talks about the aurora borealis, which is the northern lights, and the aurora australis, which is the southern lights. Australis is just Latin for southern, and boreal is Latin for north. There's a couple different words for it in Latin and for Greek, for that matter. But the main thing is the particles run into our magnetic field, and depending on their charge and velocity and all that stuff, they're going to spiral around the magnetic field and either end up coming together where the magnetic field is super strong up at the North Pole, or coming together where the magnetic field is strong down at the South magnetic pole. And that's why we see the aurora borealis and the aurora australis. I definitely recommend you read that so you'll understand some of the actual science of how those lights are made and that sort of stuff, or what actually is going on with the particle when it interacts with the atmosphere to make the northern lights. And you'll see them, they look pretty blues and greens and stuff like that. But that's it. That's enough for chapter 27. Anybody have any questions on all that? Okay, let me pull up my chat window. No one's asked any questions. I need to remember to always put that out there. I always forget. But no one's asked any questions yet. You can type them if you have them, or you can just speak out. That's all good. I don't mind you interrupting me, and I would prefer you interrupting me. Let me know if something's gone wrong. We're going into chapter 28 now, which is called Sources of Magnetic Fields. And I'm going to start off with the law of Biot-Savart because that's the most complicated thing of this entire 2 semester course. If you're doing the 3rd semester course, there might be some parts that you might find a little bit more complicated even than this, but it's not mathematically more complicated than this. This is probably the single most complicated mathematics of the entire semester is using this law of Biot-Savart. So just like there is a Coulomb's law that we could integrate to find the magnetic, or excuse me, to find the electric field around the infinitely long wire, or we could use it to find the electric field around the infinitely long wire, or an infinitely large plane, or a sphere, or something like that. We could also use Gauss's law, which was the easier way, but it had to have certain symmetries for us to actually extract the electric field out of the integral. Well, in the magnetism case, we're going to have something akin to Coulomb's law. It's even a 1 over r squared law, and that's called the law of Biot-Savart, B-I-O-T hyphen S-A-V-A-R-T. That is the more complicated version, and then there's going to be a equation called Ampere's law that's much less complicated. But again, if you don't have certain symmetries, you can't use it to extract the magnetic field magnitude out of the integram. So let me start off just by giving you the law of Biot-Savart. The law of Biot-Savart says that dB, the magnetic field, a differential amount of a magnetic field, is equal to mu 0 I over 4 pi times dl cross. Now, here's where I'm going to add something that I've done myself, and it's sort of just like what I did with Coulomb's law, but this vector is going to be RP minus RDL divided by the magnitude of the vector RP minus RDL cubed. So remember, I've got the RP minus RDL with its magnitude in the numerator. Then I've got the magnitude in the denominator cubed. So the numerator's magnitude can cancel out one of the magnitudes in the denominator so that you see it is in fact a 1 over r squared law, not a 1 over r cubed law. But that's the trick, and you can see this is a nightmare. It's got a cross product in there. It's got a subtraction of vectors. You really can't think of a much more complicated integration to calculate. So let's start off by showing you an example where we're going to calculate the magnetic field, which we already know exists. We've already discovered, for instance, that the magnetic field due to a current carrying wire can be written as mu 0 I over 2 pi r times the direction vector theta hat, which we've talked about a little bit, and I'll reiterate that if anybody needs it. But basically, the theta hat vector is always 90 degrees ahead of the radial vector. And the radial vector, in this case, we're talking about cylindrical coordinates, or you might think of polar coordinates since it's just 2-dimensional. And basically, at any point in the xy plane, if you draw a line from the origin to that point, then the direction from the origin to that point is the direction of the r hat vector. And now if you dial it in the 90 degrees ahead so that it points in the direction of increasing theta, then that would be the theta hat direction. So that's why I want you to know that, just because we want to refer to it over and over. So I'm going to start off by drawing a coordinate system that I find helpful. In this case, I'm going to draw the z-axis as vertical, and then I'm going to draw the horizontal axis. In this case, I'm going to say this is the y-axis, and then I also have the x-axis coming out of the page. So the x-axis points towards us from the screen, the y-axis is on the screen and points to the right, the z-axis is also on the screen and points upward. Now what I'm going to do is imagine an infinitely long wire that runs along the z-axis. So here's part of my wire, and here's the other part of my wire. and I'm imagining that there's a current I going upward through that wire. Okay. And what I'd like to find is the magnetic field at a distance r away. And for concreteness, I'm just going to say the point that we're looking at the magnetic field at is just going to be on that y axis. Now, you can see by the symmetry of it, I could rotate this coordinate system about the z-axis, and then if I did it 90 degrees counterclockwise as seen from above, the x-axis would be pointing to the right, the y-axis would be pointing into the page, and the z-axis would still be right where it is. Yet the magnetic field would still have the exact same direction, and that's what I'm pointing at to it being the theta hat direction. We're going to imagine also that this wire does go on for infinity, but remember, from a physics standpoint, a wire going on to infinity does not mean that it really is infinitely long. It just means you're at least no more than 1/10 of the way from the edge. So if you're 1 centimeter away, then the actual edge better be 10 centimeters away. If you're 10 centimeters away from the wire, then the end of the wire better be at least 100 centimeters away, stuff like that. So a factor of 10 is the bare minimum. I prefer 100, but a factor of 10 is a bare minimum. So this DL cross RP minus RDL gives us the actual direction. So once you cross that with the DL, now the DL is supposed to be a differential length vector that points in the same direction as the current. So I'm going to start off by showing you what the DL vector would be. So my DL vector, I'm going to write it in purple, and it's going to be like this. And I've drawn it bigger than it really should be. The length of it should actually just be like a length dz. But this vector right here is the dl vector. And we're going to call that dz k hat because it points in the positive k direction because it has to point in the direction of the current. So that's my DL vector. Now, there's also supposed to be a RP vector, and that vector is a vector that extends from the origin to the point P at which we wish to know the magnetic field. So that's my point P, and that means that my RP vector should be a vector from the origin to that. So this is going to be my RP vector. It would be really good if you guys can start thinking about exactly what that RP vector is. Can you write it out in terms of I hats, J hats, K hats, that sort of thing? And then I also need a RDL vector, and that's a vector that basically locates the differential line segment. So I'm going to use a different color here, and it's this vector right here. So this red vector is RDL. This green vector is RP. So as I advised, I asked you guys to try to think of exactly what the vectors are. I gave you what the DL vector is. Hopefully, I'm getting ready to write down the RDL vector and the RP vector, but you guys should have an idea of what it is in your mind already. If you haven't, there you go. Good job, Anahi. If you haven't, then just make sure you can figure it out afterwards or stop me if you can't. So first off, RDL, I'm going to do all these in blue. I'm just using the colors to help us. So RDL is going to be, notice it points in the positive z direction. So that means the unit vector I should use is which unit vector? Anybody? Looking at the chat. Nope. It's the k hat direction. And not only that, we already have a vector, a quantity that represents how far the DL is from the origin. It's called the variable z. So RL is going to be z k hat. Now that you know that as a trick, let's see if y'all can guess what RP is. Good job, Nathaniel. Someone tell me what you think the vector RP is. Remember it, you can see it right here. It points from the origin to the point R at which we wish to know the magnetic field. That length, by the way, is R. I know in the DL case we use the Z variable, but I don't want an X or a Z or a Y or anything in this formula, so I'm using R. And y'all said J hat. Excellent. Yes. So we're going to call this one R, and then it points in the J hat direction. Okay? So now I've got to compute the vector RP minus RDL because that's part of the formula. And you can see that's pretty straightforward. That's just RJ hat minus ZK hat. And you can see what that vector is. In fact, that vector is, let's use, I'm going to use black. So RP minus RDL is basically this vector right here. So that's RP minus RDL is that little vector there. And I think from that, since you see it has two legs, one of which is RDL and the other one's RP, I think you can therefore immediately tell me exactly what the magnitude of that vector is because that's part of the formula too. So RP minus RDL magnitude should be equal to the square root of the length of RDL we found was in fact Z. So that's Z squared. And the length of RP was R, so that's going to be R squared. So that's the actual length. Now we can go about doing the integral calculation. So B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl, which we know is z k hat crossed with rp minus rdl, that's r j hat minus z k hat, and then all of that will be divided by the magnitude cubed, so that's going to be uh, r squared plus z squared to the 3 halves power. So that's what we got to calculate. I'm going to start working over here so I can make more use of the page. I'm going to pull out the mu 0, the I, and the 4 pi. They're already out in front. But I'm also going to use the linearity of the cross product to actually pull the scalar parts of the vectors out in front and just let the operation take care of itself. But before that, I'm going to do the distributive property. So I'm going to take the integral of Z K hat crossed with R J hat. That's the first part where I'm doing the distributive property on that. Now I've got to say minus because there is a minus there. I'm going to say minus. Now the next part is the ZK hat crossed with the ZK hat. So that's going to be minus ZK hat cross ZK hat. And then all of that is still over Z squared plus R squared to the 3 halves power. Now, hopefully y'all remember enough about your cross products that whenever two vectors are parallel, then the cross product is 0, and that's what we get for zk hat cross k hat, because that's going to become z squared times k hat cross k hat. And remember, the magnitude of a cross product is the magnitude of the first vector, which in this case is 1, times the magnitude of the second vector, which in this case is also 1, times the sine of the angle between them. But in this case, the angle between them is 0, and the sine of 0 is 0. So that's why that came out. Now I can continue on and say that I've got mu 0 I over 4 pi times the integral. This is where I'm going to use the linearity of the cross product. I'm going to pull out the z and the r out in front, and then I have k hat cross j hat. Now, k hat cross j hat, you can use your right hand rule and you can use this coordinate system right here. You see k hat is up and you see j hat is to the right, and that tells you my thumb is pointing. Again, if I align this with my page, my thumb is pointing into the page, and that's the negative I hat direction. So k hat cross j hat is actually negative I hat. Okay. And I still have the denominator on there, so I'm just going to write dot 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 to hide the fact that I forgot to write it down first. All right, now that I have that, I'm going to go back and start over here and say B is equal to mu 0 I over 4 pi. Now I can see, where did my DZ go? DL, I had that was DZ. Oh, that's what it was. Sorry about that, everybody. I don't know why I wrote this. I wrote it correctly over here. I wrote DZ, but over here I just wrote Z. That's supposed to be DZK hat, which makes that a problem because that's a D. This little guy in here was supposed to be a D. Let's fix that real quick. Uh, and then this one, of course, is supposed to be a DZ. I'm going to write the R in front of it so it looks a little more normal. So I'm going to write R DZ like that. Okay, so now we're back up and running. So now I have mu 0 I over 4 pi times the integral of R dz times negative I hat. I'm going to pull out that negative I hat on the next iteration and just make it like a constant. And I still have in the bottom z squared plus r squared raised to the 3 halves power. And now I can see that the integral is going to be with respect to z, of course, and this is not that kosher, but the r is, meaning it's not very easy to integrate. I'm going to have to use a trig substitution. So the r and the I hat and the negative sign I'm going to pull out in front. So now I got negative mu 0 I r over 4 pi I hat times the integral of dz over z squared plus r squared to the 3 halves. I'm going to say let z equal r tangent theta, then dz is equal to r secant squared theta d theta, like that. And I'm not going to mess with the range of integration. I know I'm going to integrate from z equals negative infinity to z equals positive infinity. Uh, now that I'm changing the variables, I could change the limits of integration to those variables, and I will do that. I'm just not doing that yet. So now I can go ahead and replace the dz with r secant squared. So I've got negative mu 0 I r over 4 pi integral, oops, left off the I hat, integral of, now dz is going to become r tangent, or excuse me, yeah, r tangent, oh, r secant squared, excuse me, r secant squared theta d theta. And now down in the bottom, I'm going to have r squared tangent squared theta plus r squared, all of that raised to the 3 halves power. And the whole purpose of us doing that is I can factor out an r squared now. And when I factor out that r squared, it's going to leave a 1 plus tangent squared in parentheses times r squared, and all of that under a 3 halves power. So r squared to the 3 halves power becomes r cubed in the bottom. And now I have minus mu 0 I. I already had an r on top, but when I substituted for the dz, I got another r, so that becomes r squared on the top. and then 4 pi on the bottom. But when I factored out that r squared from the two terms in the bottom, that gave me r cubed in the bottom. So I'm going to put r cubed down here as well. You can, of course, see that the r squared is going to cancel out and leave just a single r in the bottom. Now, with that, we have the integral part, and the integral part is secant squared theta d theta over 1 plus tangent squared was what was left under the 3 halves, but 1 plus tangent squared is secant squared. So we're going to, and that's just a trig identity. So I've got secant squared to the 3 halves power. That means it's going to become secant. Oop, left off my I hat again too. That means it's going to become secant cubed in the bottom and secant squared on the top. So just like the r's, it's going to leave just a secant in the bottom. That secant in the bottom is the same thing as a cosine on top. So now I can write negative mu 0 I over 4 pi r I hat times the integral of cosine theta d theta. And of course, now I'm going to integrate from theta equals negative pi over 2, because if you notice, since tangent theta was z over r, from z equals r tangent theta, we can see that tangent theta is equal to z over r. So that tells us that this angle right here is the theta that we're talking about. If I want to look straight up at an infinitely tall building, I have to look literally straight up at 90 degrees. And then if I look at an infinitely deep hole, I have to look straight down. So that's why I'm integrating from negative pi over 2 to pi over 2. So now we can go ahead and compute all that. I've got negative mu 0 I over 4 pi r I hat, and the integral of cosine, since the derivative of sine is cosine, the integral of cosine is sine. So this is going to be the sine of pi over 2 minus the sine of negative pi over 2. Now the sine of pi over 2, if you look at your sine function, which looks like this, you see pi over 2 and negative pi over 2. The sine of pi over 2 is in fact 1, and the sine of negative pi over 2 is in fact negative 1. So I've got 1 minus a negative 1, which gives me a positive 2. So I can now realize that the magnetic field B is just negative mu 0 I over 2 pi r, and that points in the negative I hat direction, which is into the page. If you notice, at that point at the y-axis, the variable theta that we're used to from polar coordinates would be 90 degrees. And to increase the theta, you would actually go continue turning it into the page, which is exactly the direction of theta hat. So in general, by the symmetry of this, we can say that B is actually mu 0 I over 2 pi r in the theta hat direction. And that's our answer. Anybody have any questions on that? Notice this is about as difficult. It's a little bit more difficult than the first integration we did in chapter 22 when we were covering Coulomb's law, and we did it for an infinitely long line of charge that was uniformly distributed, and we ended up getting lambda over 2 pi epsilon naught, but it pointed away from the wire. In the magnetic field case, it points around the wire, which is why the theta hat works so well. Just in case you are a little lost by this idea of theta hat, let me just take a second and give you an idea what theta hat is in terms of the XY coordinate system. So here's the X, here's the Y. By the right-hand rule, the Z would have to be coming out of the board. So we would imagine if the current was on this axis, it'd be coming straight out the page. And I think that's consistent with the right-hand rule you learned in Faraday. But here's the wire, and here's the current coming out of the page, and therefore you know that you use your right hand. Remember, when you're trying to find the magnetic field due to a current carrying wire, you use your hand in this way. You point your right thumb in the direction of the current, and then you wrap your fingers around the wire, and the fingers of your right hand tells you what direction the tangent vectors of a circle are. So now what we're going to do is imagine a circle around the wire, and it's going to be centered on the wire so that all the points on the circle will be the same distance away from the wire. And we've already learned that the distance away from the wire is or the magnetic field is inversely proportional to that distance. But since that's the only variable it depends on, that means the magnetic field will be a constant in each of those directions. So, or in each of those points. So right here, the magnetic field points that way. Uh, and it actually tilted a little bit because the stupid program that I'm using was trying to make prettier art than I had. So it would point into the up there. Right here, it would point this way. Right here, the magnetic field would point that way, and right here, the magnetic field would point that way. Right here, it's a tangent vector, and all these vectors, I'm trying to draw them correctly, but all these vectors should have exactly the same length. I'm not doing as much work as maybe I should to make sure they're the same length, but I want you to know that they should be because they're all a fixed distance r, and we know the magnetic field is mu 0 times I over 2 pi r. So if the r is the same and the I is the same, which obviously they have to be, that means all these magnetic fields are right. Now, let me show you what direction theta hat is. So if, for instance, we have a point right here, then r hat points that way, and theta hat points in the direction of increasing theta. So you see theta hat would be that way. Similarly, if this was your point, let's say right here, then r hat would point that way and theta hat would point this way. Similarly, if your point was right here, theta hat would point this way and r hat would point that way. And if your point in space was here, theta hat would point that way and r hat would point this way. If your point were here, theta hat would point that way. If your point were here, theta hat would point that way. So I think you can now see, given the way theta hat's defined, it's clear that the direction of the magnetic field is in fact the theta hat direction. Remember, all it is you draw a line from the origin to the point in space at which you wish to put the unit vector. That line, if you travel from the origin to that point, you're going in the direction of r hat. So that allows you to define what r hat is. And then you go to the side of r hat that represents increasing theta. And remember, theta is always measured counterclockwise, is the positive direction for theta measured from the positive x-axis. So you always go in the increasing theta direction from r hat, and you always go 90 degrees. So it's always going to be 90 degrees ahead of the r hat vector, and now you know what it is. And specifically, just because it will come in handy in your statics class, for instance, r hat is actually cosine theta I hat plus sine theta J hat, which you can work out easily just by realizing the diagram. And then theta hat you can work out easily as well. That's negative sine theta I hat plus cosine theta J hat. And if you want to work that out, it will help you greatly in statics and dynamics and all that good stuff. Eventually, once you figure out how they're avoiding teaching it to you. But if this is the x-axis and this is the y-axis right here, then if you take a single point, let's say our point's right here, this distance is the r, and this angle right here is the theta. This vector is r hat, and perpendicular to that is the vector theta hat. Now we can draw another coordinate system at this point so we get an idea which direction is x and which direction is y. And you see from that that clearly this angle is theta. So you can now break this up into components. This component is going to be the magnitude of r hat times the sine of theta, which is just 1 times the sine of theta. And this component is the magnitude of r hat times the cosine of theta, which is just 1 cosine theta. So now you see how I got the cosine theta is the x component and the sine theta is the y component. Now, additionally, since this angle theta is how far r hat is tilted away from the x-axis, that means theta hat is also tilted away from the y-axis by an angle theta. And you see that even though we're in the first quadrant, the y component of theta hat is negative, but the x component is positive. And you can see that the x component of theta hat is actually going to be negative 1, because the magnitude of theta hat is 1 times the sine of theta, and the y component of theta hat is positive 1 times the cosine theta. Now you can see why I said theta hat was negative sine theta I hat plus cosine theta j hat. And in case you forget all that, there's also the fact that dr hat over d theta is actually equal to theta hat. So that's another way. If you can figure out r hat or memorize r hat, you can easily get theta hat from it. That's going to come in handy over and over again. Even though it's a little more than most teachers do with the 241 or 242 course, I certainly find it reasonable to do in the 242 course. But we only have 5 more minutes. I had some other things that I wanted to show you, but I think it's better that I spent the time covering all this stuff. When we get back next time, and I might send you a video or two to watch just to prep, even though I'm going to go over the same stuff. But when we meet next time, I will finish up chapter 28 by going over 2 more problems, or actually probably 3 more problems using the law of Biot-Savart, and then I'm going to introduce you to Ampere's law. Just for the record, Ampere's law says the closed integral of B dot dl is equal to mu 0 times I enclosed. Remember, Gauss's law was the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That is a surface integral, whereas Ampere's law is a path integral. So this is Ampere's law in integral form. And the Gauss's law is a surface integral, like that. But notice how both of them have circles on their integrals. That means in the Gauss's law case, it had to be a closed surface that has a clear inside and outside. In Ampere's law, it has to be a closed path, meaning one that starts at some location, does all sorts of stuff, but returns back to that same location. We're going to call that an Amperian loop, just like we called the surfaces that we used in Gauss's law a Gaussian surface. So that's what we're going to do. And notice they both have an enclosed quantity. And for us, Q was given by dq is either equal to lambda dl or sigma dA or rho dV. In this case, I can be really 2 things, and your book doesn't even mention one of them. Di can either equal J dA, or it can equal K dl. But I tell you, the KDL very rarely does anybody ever do anything with that, and it's technically J and K are both vector quantities. But that's what we use in lieu of that. The good news is we're in this class we're not going to use KDL at all, but in this class we will use J.DA. So. That should get you started. I don't think I have a chapter 28 homework. I don't think that's due until next weekend, anyways. But this definitely is me telling you it's not going to be due this Sunday, even if it says it's due this Sunday. Okay. So, and I think you've got quite a bit to work on with chapter 27. You can already finish that, of course, but with chapter 28, it's going to obviously take a little bit more before you can solve problems for that. So that set's definitely going to be moved to next Sunday at the earliest. You folks are free to go. Don't forget to chat me your first and last name if you haven't done so already. I'll wait till the last person leaves in case anybody has any questions. I think Giovanni and I were working on a problem that he might still want to work on, so I'll do that on this next page. Okay, I'm going to draw that circuit, Giovanni, while we're waiting for people or whatever. I'm going to draw that circuit again and just start over and show you how to work it. See if that helps. So we have a 12-volt battery this way, and then that runs into a 1 ohm resistor, and then that runs into an 11 ohm resistor, and then we break off into that right there is one single wire, so that's what I'd call a leg of the wire, and the ends is what I call junctions or nodes. Now up from there, we run into a 12 ohm resistor. That was a really badly drawn resistor, but that's okay. And then we run into a battery, and this too is a 12-volt battery. And then we run into another 1 ohm resistor. And then we run into a 22 ohm resistor, which I'm going to put over here instead of on that other wire. So that's 22 right there. And then down here, we're going to run into a 15 ohm resistor. And then we're going to run into a 6-volt battery, 6.0. And then we're going to run into a 1 ohm resistor. And then we're going to run into a 18 ohm resistor. And for concreteness, your book went ahead, or the homework system went ahead and defined their current directions and current names. So this is I2 going this way. This is I1 going this way. And this is I3 going this way. So just to show you the upper loop, I'm going to say plus 12.0 because I'm going from the dot right here. I'm going from this dot this way like that. That's what I'm doing for the upper loop. So that's 12. Notice I'm going the direction of the current, so the resistor is a voltage drop, so that'll be minus 1 I2 minus 11, or excuse me, yeah, 11 I2. And then now when I go up there, tang this left, I'm going the direction of I1. So the 12 ohms is another voltage drop. So that's 12 I1 and then plus 12.0 and then minus 1 I1 and then minus 22 I1, and we're back where we started from, so we say equals 0. So I can combine like terms, and that's going to give me 24.0. And then with the I2s, I can see I've got 1 and 11, so that's going to be minus 12 I2. That takes care of this one and this one. And then I've got, and I've already taken care of that 12 and that 12. Now I've got 12 I1 minus another I1, so that's negative 13 I1. And then 22, that would be negative 35. I1 is equal to 0, and I'm going to call that equation 1. Now I'm going to do the lower loop, and the lower loop, I'm going to do this one this way. Okay, so the lower loop, the first thing I encounter is the 12-volt battery, so that's plus 12, and then minus I1, it's actually 1 times I1, and then minus 11, ooh, I2, sorry about that, and minus 11 I2. Now notice when I get to that bottom leg, I'm going the opposite direction of I3, so the 18 is going to be a plus 18 I3 plus I3, because that's 1 I3. And now I'm going from the long leg of the battery to the short leg, so that's a decrease in voltage, minus 6.0. And again, I'm still going against the direction of the current, so that's a plus 15 I3, and that was I3 as well. And now I'm back to where I started from, so I can say that's equal to 0. And this is going to give me 12 minus 6 is 6. So I'm going to say this is 6.0. That took care of those two. Minus 12 I2, that takes care of those two. And 18 plus 1 would be 19, plus 15 would be 29, plus 5 would be 34. So this will be plus 34 I3 is equal to 0. So that's going to be equation 2. And we can see that I2 plus I3 is equal to I1. So I2 plus I3 is equal to I1, and that's going to be our equation 3, and that came from this node right here. If I did this node, you'd probably call it I1 equals I2 plus I3, but you can see that's the same equation, just written in the opposite direction. Now, what I suggest you do is we have a common I2 in equations 1 and 2, so I'm going to solve for the other variable in both cases. So equation 1 prime is going to be me solving equation 1 for I1. So I1 is going to be equal to 24 minus 12 I2 over 35. And I find this most useful to go ahead and make this into decimals or fractions. So 24 divided by 35 is 0.687, or excuse me, 6857, minus 12 divided by 35 gives me 0.3429, so 0.3429 I2. So that's my I1. Now I'm going to give you equation I2, or excuse me, 2 prime, and that's going to, oops, I just did that. No, I did it right. Okay. So now I'm going to use 2 to solve for I3. So I3 is going to be 12 I2 minus 6.0, and then divide all that by 34. And 12 divided by 34 gives me 0.3529, so 0.3529 I2. And then 6 divided by 34 gives me 0.1765, like that. And now I'm going to plug 1 prime and 2 prime into 3. And if I didn't make any careless mistakes, it should be pretty straightforward. So I got 0.6857 minus 0.3429 I2 is equal to, oops, that was supposed to be I1. So that's equal to, now I2 is just I2, and then I3 is 0.3529. Oops, I just dropped. Oop, both of them are 3529. Okay, that's cool. 3529 I2 minus 0.1765, like that, and that is I2. So now we see we only have I2 involved here. I'm going to put all the I2s on the right and all the numbers on the left. So 0.6857 uh, is going to have added to it plus 0.1765. That's going to give me 0.8622 on the left. And now I'm going to take I2, which has a coefficient of 1. I'm going to add to that 0.3529. And I'm going to add to that 0.3429. Yep. Hopefully that's not an error. It's weird how closely similar they are, 3529 versus 3429. So adding all that, I get 1.6958 I2. So that tells me I2 should be equal to 0.8622 divided by 1.6958, and that gives me 0.5084, which the solution set says 0.51, so that looks correct to me. Now that I have I2 and I've got the thing solved for I1 and I2, I just plug those formulas in and that gives me I1 and I2. So I1 should be equal to 0.6857 minus 0.3429 times 0.5084. Notice if you happen to found this negative, you've got to still plug that negative in until the problem is completely done. So you just got to stick with your signs that you get. I'm going to say 0.6857 minus 0.3429 times 0.5084. That gives me 0.5114 amps is equal to I1. So that's also what the homework set had was 0.51. And then I3 is, it was supposed to be 3 times 10 to the negative third, so 0.003. But let's see what it comes out to be the way we've done it. 0.3529 minus zero point 0.1. Oops, sorry. I've got to multiply by that first. So 0.3529 times 0.5084 minus uh, 0.1765. So 0.3529 times 0.5084 minus 0.1765 gives me 0.002914 amps, which does look exactly like the 0.003 that they suggested. Did that help you, Giovanni?
Yeah, I see where I went wrong. So since I was going counterclockwise for the bottom loop, I put 11 I2 as negative.
Oh, gotcha.
Uh yeah, and I think that's where I went wrong.
Yeah, if you got signs that are inconsistent with what I have, they could all be exactly the opposite or they can all be exactly the same. But if they're mix and match, then that's a good indicator that you made a boo-boo.
Yeah, because I have my the internal resistance as positive, but then the 11 I2 as negative.
Yeah, yeah, that's what I thought I heard the last thing we said just before I went into the class. So that's cool. Anything else you need, Giovanni?
No, just that. Also, the lecture that you did today, that you're gonna post that on YouTube, right?
Yeah, yeah, I post it. I usually post it the same night, but sometimes I don't get to the till tomorrow morning. I'm not sure which one will be today, but it'll either be tonight or tomorrow morning.
Okay, yeah, because I just barely started chapter 27, so a
Gotcha.
lot of what you said didn't make sense. The math made sense, but
Yeah, it's
um,
not a trivial subject. I honestly, guys, I don't know how you folks succeed in this class online. I'm not sure. I at least at your level when I was you know in freshman or sophomore in college, I'm not sure I could have done a 242 online. So you know, I owe you praise for being able to do as well as you're done. Did you notice that I posted three extra credit assignments that's supposed to increase your face-to-face test two test grade?
yeah, and I'm probably gonna need those because I know I didn't do uh well on the test, so
Well, one thing I want to point out is because I went through sequentially leading you through that, and I've not since learned that a lot of people hadn't watched any of the videos of my class. They were completely blown away. But if they were able to see that I was just trying to get you to derive the capacitance for an infinite parallel plate capacitor, and they did the derivation, I'm going to give you full credit, whether it's no matter what those individual 6.25 points were for each of those questions leading up to it. If there's eight of them, it'll be 8 times 6.25 points if you do it all right, even without following my steps. So your grade might be a little better, but that's what's taken me so long. I haven't finished grading them yet. I should finish today or tomorrow on those, and then when you have that, it's the extra credit points everybody should do. Okay.
yeah. And how many does that increase your?
The way I've got it, let me stop sharing this for a second. I've got it written on a little text document up here. I'm just trying to find the text document now. Text it. There it is. Here it is. Okay, so students that make a 50 or lower can earn up to a 67. That means if you get 100% on each of the three extra credits, then the average of three 100s will be 100, and you'll get basically all of the points that bring you up to a 67. However, if you had like a 50 originally and you only get 50% right on the three, out of the average of the three is only 50, then you'll go halfway from 50 to 67, which is only about what, eight and a half. So you'd end up getting a 58.5. If you
Mhm.
made a 51 to a 60, you can get up to a 77. If you made a 61 to a 70, you can get up to an 80. If you made a 71 to an 80, you can get up to a 90. If you made an 81 to a 90, you can get up to a 93. And if you made a 91 or higher, you can only have 2 points added to your test.
All right. So you said 50 or lower, it does what?
At 50 or lower, it brings it all the way up to a 67
Okay.
if you get 100.
Okay.
Okay?
And are these? I remember I looked at them last night, and I think what was it? You have unlimited attempts on it, right?
Yeah, unlimited attempts, and it's due, I think I said Tuesday. If you find that you still need more time than Tuesday, send me an email like Monday and let me know. I don't mind pushing the deadline back. I just don't want people just missing it. So if y'all feel like you need more time, just send me an email and I'll give everybody more time. But I think y'all should want to do it really quickly, and I think you should want to have it done by Tuesday. But if not, just let me know before Tuesday so I don't have to, you know, end up giving you a zero and then reconsider doing it and all that stuff.
I got you.
All right.
All right. And one final thing. So this one's just like the wording of them.
Uh-huh.
So I know that the next online test, the one that's due on Tuesday, it's mainly on chapter 26 and 20 or just 26, right? 25 and 26.
Yes, but it is comprehensive like all of them are. So,
And so then like I know that the next face-to-face test it's just titled 27 and 28. So is it just gonna like mainly focus on that?
yeah, it'll be 27 and 28. But what I do is when I notice that people miss something from chapter 20, for instance, or chapter 19 or something, then I make sure I put some of those questions like what they missed on the previous test. So, what you need to do is look at your face-to-face test one, find anything you didn't feel that confident about, and then look at face-to-face test two, find anything you didn't feel confident about, and then address those, learn how to do those problems because they might appear on the next test.
hmm And just to this is just a suggestion from
Gotcha.
me.
Hmm.
I think one thing you could do is like even after the tests are done, if you could leave like the practice tests open, like the face-to-face practice tests
Gotcha.
open.
Yeah, the reason I don't do that is because I've discovered that my students don't take the practice tests very often. In fact, if I don't give them extra credit, I get very little turnout. But by doing it and only giving them the extra credit if they get it done before the test, then I get usually about 20 out of 24 students will take it. Uh, so I don't want to go doing that, but there are other tests. You still have the exact same test, but per chapter available to you. It's just you can only focus on one chapter at a time with that. So that's why I don't keep them the whole practice tests open. But I do have individual chapter tests that you can take repeatedly to just
Yeah.
work on a single chapter. Okay.
All
Well,
right.
thank you for the
Mm-hmm.
suggestion. I completely understand.
Yeah. All right.
All
Well,
right.
that's all.
All right. Thanks, Giovanni. Have a good one. I appreciate your
All
help and
right.
I appreciate all your advice and stuff you tell me. That helps me.
All right. Have a good night.
You too. See you, bud.